So chapter 4 is on functions. Given a set D called the domain, and a set R called a range, a function, and here's the notation, F colon domain to range, is an assignment of one range element to each domain element. This is written as, so if X is in the domain, the range element assigned is F of X, which is in the range. Okay, so we're going to be talking about functions in very formal terms here, which is how they're discussed in mathematics. For the most part, in this class and in modern algebra 1 and 2, and in like advanced linear algebra, I'm not sure about real variables, I've never really taught it. This is the most confusing thing for students, functions. Functions, different types of functions, and how to deal with functions. Okay, so a little extra time and consideration on the subject would be worthwhile for you. So, for example, and it's not the same sort of thing like you mean by a function in calculus. Or in pre-calculus. I mean, when you just say like f of x is equal to x squared plus 1 or something like that. I mean, that is a function. But this is something more general, what we're talking about. Right? This is when you say f of x is equal to x squared plus 1, we'll do that as an example. So typically the way you might draw something, a function, you put a set for the domain, a set for the range, maybe put some elements in the domain, and then a few elements in the range, A, B, C, D, and then F will follow the arrow essentially. Okay, so here the domain is 1, 2, 3, 4, 5. The range is A, B, C, D. F of 1 is A, F of 2 is A, F of 3 is C, F of 4 is B, F of 5 is C. And notice that nothing goes to D, and that's just fine. So in such a diagram, every domain element has exactly one outgoing arrow. The range elements can have any number or 0 incoming arrows. The range element that's assigned to the domain element is unique. There's only one outgoing arrow. But, the same different domain elements can be given the same range element. That's not a problem. Another example. All right, so R is the set of real numbers. Right, when we write f of x equal to x squared plus 1, or f of x equal to cosine of x, or what else? F of x equal to e to the x, right? These all represent for assigning for a function f from the set of real numbers to the set of real numbers. What about if I said like log of x? Is that a function for the real numbers? So I mean we list a couple functions here: f of x equal x squared plus 1, fx equals cosine x, fx equals e to the x. What about fx equal to log x?
Yeah, that'd be a function.
Not for all real numbers, right? Just for the positive ones, right? Is a function.
Yeah.
Because it has to work for all the domain elements, from R plus to the whole of R. Right? It has to be defined for all real numbers in order to be a function on the real numbers. So, like if you remember those exercises from Calc 1 and from Calc 3, here's a function, tell us what the domain is. And the domain was the way they defined it in those calculus books, the largest set of real numbers on which it's defined. Although it doesn't have to be that. You can always restrict the domain to something smaller. That's fair game. What about these? Given any domain D, right, a predicate d of x is a function, or not d of x, predicate p of x is a function p from the domain to what? What's the range? When you have a predicate, you plug in a domain element and what do you get? The result is
Would it be the truth value?
Yeah. So the range is just TF, true, false. It's a logic valued function. You have whatever domain it is you're talking about, and then the range element is just a logic value. Hey guys, let's take just a 2-minute break, okay? I'll be right back. Definition. So, given a function f from domain D to range R, and a subset A of the domain, the image of A under F is written like this: f of A, it's the set of all f of x such that x is in A. So, for example, we go back to this little arrow diagram we got here. If we let A be equal to the set 1 and 2, then the image f of A is what? Maybe we'll just avoid confusion with letters. We'll let x be the set 1, 2. Then the image f of x is what? The set of all elements x, f of x, such that x is in A. And that's a subset of the range, of course.
So would this just be little a?
Just little a, yeah. So before the example, note that f of A is a subset of the range. So this is the set, just little a. How about f of D itself, the image of the whole function?
ABC.
It's just ABC. Okay, note the image of the whole domain of f from D to R, instead of being written as f of D, it is written as just the image of f, just the image of the whole function. So instead of writing f of D, sometimes folks will just write the image of f. All right. How about this? Let's say f of f goes from the set of reals to the set of reals. And f is defined by f of x equals x squared plus 1. So in this case, the image of f is equal to what? So you take the entire set of real numbers and you throw it into that function, and what real numbers do you get out?
If I was gonna do like a rule for a set, would it be okay to start with like x such that x is like greater than or equal to 1?
Yeah, you could write it as in set builder notation, if that's what you want to say, right? It's the set of all x in R such that x is bigger than or equal to 1. Right, well, or you can also use this like 1 to plus infinity sort of notation. How about the following? How about f of the interval from 0 to 2? If we did, or how about the interval -1 to 2? Closed interval from -1 to 2. What does that give us? The image of that.
Why could the first set not be negative?
X squared is always positive, right?
Oh, I thought you did cube. Sorry.
Yeah. Yeah, that's a square. So f of the interval from -1 to 2, if you plug in all the elements from -1 to 2 into this function, what do you get out?
One's a 5.
1 to 5. Okay. Here's a little proposition. What's a proposition? Well, I mean, when we write it like this, proposition is just a statement in the English language. When we write in mathematics, there's kind of three types of statements in mathematics, like major statements. There's theorems, there's lemma, and there's propositions. So, what they mean in a sort of a literary sense in mathematics. I mean, a theorem is a major result of independent interest. So, like Pythagorean theorem, the law of cosines, the fundamental theorem of calculus, fundamental theorem of algebra. These are all theorems. The four-color theorem, all theorems. Propositions are lesser statements. Statements that, have their own interest, but are, of lesser importance. I mean, that's a subjective value judgment, but it's fine. That's just what people say. And then a lemma is typically a proposition that is not of independent interest. It is only used as a precursor to proving a theorem. So here, let's write proposition. It's not a big formal theorem. It's just proposition. Okay, so let f be a function from a domain D to a range R, and let A be a subset of B, which are both subsets of the domain. Then, I guess we could say it as an if-then. So if f is a function from D to R, and A is a subset of B, is a subset of the domain D, then the image f of A is a subset of the image f of B. Okay, so let's write out a proof of this. Okay, so, well, to prove an if-then statement, you remember an if-then statement is only false when the hypothesis is true and the conclusion is false. Okay, so here we're going to assume the hypothesis is true. We're going to do a direct proof and then show that the conclusion must be true. Okay, so assuming that A is a subset of B is a subset of D, okay, if X is an element of F of A, then by definition X is equal to what? So I want to show that F of A is a subset of F of B. All right, so assuming X is an element of here, I got to show X is an element of here. So, take an element X in f of A. By definition, X is equal to what? What's f of A?
F of x such that x is in A.
Yeah, f of some little x such that X is in A. Of course, I'm using the element of the letter X twice. Let's not do that. So if, what should we call it? Z is in f of A. Then by definition, Z is equal to f of X for some X in A. Okay, because A is a subset of B, X is also an element of we assume that A is a subset of B. Sorry, say that again?
A.
Yeah. Therefore, by definition, Z equal to f of X is an element of the image of B, because X is in B. And that's that. All right, so